This is the lecture for Section 7A, Fundamentals of Probability. Outcomes are the most basic possible result of an observation or an experiment. For an example, if you toss two coins, one possible outcome is head, then tail. Another possible outcome would be tail and head. An event consists of one or more outcomes that share a property of interest. For example, if you toss two coins and count the number of heads, the outcomes from above, head, tail, and tail, head, both represent the same event of one head and one tail occurring. Suppose we describe a day's overall weather as either sunny or cloudy. List all the possible outcomes for the weather on 2 consecutive days. If we're only interested in the number of sunny days, what are the possible events for 2 consecutive days? So the 2 questions first, starting with listing all the possible outcomes. So we'll let S represent sunny and C represent cloudy. That means there's 4 different possible outcomes that could happen. We could have sunny and sunny, sunny then cloudy, cloudy then sunny, or cloudy and cloudy. The second part asks about us only looking at the number of sunny days. Well, if we look at it that way, we can either have no sunny days, 1 sunny day, or 2 sunny days. So no sunny days would happen when we have cloudy, cloudy. 1 sunny day would happen on the cloudy, sunny, or sunny, cloudy days. And then 2 sunny days would happen when they're both sunny, sunny. So we can see 2 different ways that we can look at this. The outcomes are the individual pieces, C, 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 S, 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 and S, C. And then we can also look at how many S's we have or how many C's we have. Anytime we talk about probability, the probability of an event, we're always going to see it probability like P of, and then we're going to fill in inside parentheses here, whatever it is we're looking for. The result always has to be between 0 and 1 inclusive. That means it can be equal to 0, it can be equal to 1, or it can be any number in between there. 0, if your probability is 0, means it's absolutely impossible to occur. And then as we work our way up here, we're going to get unlikely. As we get towards 0.5, that's half chance. Then as we get closer and closer to 1, we get more and more likely to happen. And if your probability is 1, that means it is certain to happen. There is no other option besides what you have asked for. The first type of probability that we're going to talk about is theoretical. And theoretical involves looking at things that have equally likely outcomes. So, for example, flipping a coin, rolling a die, drawing a card out of a deck of cards. All of those things have equal likely probabilities. So, the first thing you're going to do is count the total number of possible outcomes. The second thing you're going to do is, among all those outcomes, count how many ways that whatever you're looking for can occur. And then we can calculate our probability by taking the number of ways that that item occurs divided by our total. We're going to apply the theoretical method to find the following probabilities. So this first one, we have flipped 2 coins. And you can see here we have no heads, we have 1 head, 1 head, and then 2 heads because it matters which coin had the head on it. How many ways can we get exactly 1 head when you toss 2 coins? Well, this is one way to do that. This is the other way to do that. So there are 2 possible ways out of 1, 2, 3, 4 total outcomes. And 2 over 4 is also 1/2. The second question, we've got a 6-sided die, and we want to know the probability that we roll a 3. Well, a normal die, has the probability the same for every single number. We've got the same chance of rolling every single number. So 3 occurs 1 out of 6 possible numbers. Another example, there are 52 playing cards in a standard deck of cards. There are 4 suits known as hearts, spades, diamonds, and clubs. Each suit has cards for the numbers 2 through 10, and then a jack, queen, king, and ace, for a total of 13 cards in each suit. So that means there will be 13 hearts, 13 spades, 13 diamonds, and 13 clubs. Also know that the hearts and diamonds are red cards, these spades and clubs are black cards. If we wanted to find the probability that we draw a spade, well, how would we do that? Well, we have 13 of every suit. So there are 13 spades out of 52 total cards. That reduces to the fraction 1/4. So let's think about that in another way here. Spades is one of the 4 suits. And that's exactly the reduced fraction we got there. If it helps, you can easily Google a image for all the decks of cards, all the cards in the deck of cards. And when you're working on these problems, you can use that to help you. This example is about birth month probability. You select a person at random from a large group attending a conference. What's the probability that the person has a birthday in July, assuming there are 365 days in a year and births are equally likely to occur on any day of the year? Well, we're going to keep using the same method. Every day of the year has the same chance of occurring. So we know we have 365 total possible outcomes. So we have to look at the month of July. The month of July has 31 days. So then to create our probability on the next slide, you'll see. Gives us 31 out of 365, because there's 31 days in July out of 365 total days in the year. And if I were to reduce that into a decimal, that's about 0.0849. And that's slightly more than 1 in 12. The reason being is July is one of the months with 31 days. There are months with only 30 days, and then you have February, which only has 28 days. So can't just say it's 1 in 12 because not all of the months have exactly the same number of days, but it is close to that value. The next type of probability we're going to look at is relative. And this is more of we're doing an experiment and we are counting how many of each of these different things occur. So maybe I give you a bag of M&Ms and I tell you to count how many reds are in your bag of M&Ms. Every single one of us is going to get a different number of red M&Ms and probably a different number of total M&Ms in our bag. So what we're going to do for this, it's going to be similar. It's going to be the number of ways you want to find that item out of the total number of items that you have. So for example, if it was how many red M&Ms out of the total, you would have to actually count. So this is going to be a little bit more of an approximation based on an experiment that we are doing. For this problem, we are going to still work with coins, but our goal is in this time, we are going to actually flip the coins. So we're going to flip 2 coins and we're going to mark down, did we get no heads, 1 head, or 2 heads? And then we want to evaluate their probabilities. Do they look close enough to the theoretical, what we would expect to happen? So we're going to flip 2 coins 100 times, and this is what happens. We got no heads 22 times. We got 1 head, that means 1 head and 1 tail in any order, 51 times. And then we got 2 heads that happen 27 times. So then we're going to look at on the next slide what these probabilities are for the experiment and how they compare to what should happen with coins. From theoretical probabilities, we know that we should get no heads 1 of the 4 times. So that's the option tail, tail. 1 head is going to happen twice out of the 4 times because we get tail then head or head then tail. That's our 2. And we get 2 heads 1 out of the 4 times. So the probability should be 1/4, 1/2, and 1/4, or relatively close to that. Our sample, we had 22 out of 100, or 0.22. That's pretty close to 0.25. 51 out of 100, or 0.51, is really close to 1/2. And 27 out of 100 is 0.27. Again, is really close to that 20.25, that quarter. So our experimental probabilities are close to the theoretical probabilities. So it looks like our coins are good coins here. And the more you run those tests, the more I flip those coins, I should get even closer to these theoretical probabilities up here. The local weather station has been correct for 15 of the last 27 days. Based on this fact, what is the relative frequency or probability that the forecast will be accurate tomorrow? Well, they've currently been correct 15 out of 27 times. So if we want to find the probability that they're going to be correct, well, we're going to use that value, 15 out of 27. And I can reduce that. Let's see, both of those are divisible by 3. 15 divided by 3 is 5. 27 divided by 3 is 9. So 5/9, and that's 0.555. So 5/9, or 0.55 chance that they will be correct on their next weather prediction. So far, we've talked about these first 2 probabilities. The theoretical probability is where each outcome is equally likely. Relative frequency is when you're going to do an observation or an experiment and you're going to actually keep track or count the number of ways each type occurs. The last one is called a subjective probability, and that's just going to be an estimate. I believe it's going to be this probability just because of either I have knowledge of it or I'm going to claim I'm a psychic, so this is what I know it's going to be. So let's identify each method based on the situation. If someone says, I'm certain that you will be happy with this car, that is subjective. They are just making an assumption or trying to sell you something here. They're just saying, I think you're going to be happy with this. There is no evidence to back that up. It's just a statement. Next one. Based on housing data, the chance that someone will move to a new residence during the coming year is about 1 in 8. So this says based on data. We're basing it on data, numbers that we've counted and collected. So that's our relative probability or relative frequency. C, the probability of rolling a 7 on a 12-sided die. Well, if you've created your 12-sided die correctly, each side is going to be equally likely. So it's going to be theoretical probability, and 7 happens 1 out of 12 of those times. If we know the probability of an event occurring, we can find the probability of it not occurring. So if we know that P of A represents the probability of our event occurring, then the probability that it does not occur is going to be 1 minus that value. So let's look at that die problem. We knew that the probability of rolling a 7 on a 12-sided die was 1 out of 12. So if we want to find the probability of not a 7, well, that's every other number on the die. That is the remaining 11 out of 12 numbers, which is exactly 1 minus 1/12, giving me 11/12. What we can do then is if we have theoretical or relative probabilities, we can create what is called a probability distribution. And it's basically just going to be creating a table model that shows us the probabilities of all the different outcomes that we have. So the first thing you're going to have to do is list all the outcomes. Usually a table is a great way to do that. And we're going to identify all the outcomes that represent the same event and determine then the probability of each event. And then we can fill in all those values in our table. And in the end, the sum of all the probabilities should be equal to 1. So let's look at the example of rolling 2 dice, and we want to add the dice together. So pretend you're playing Monopoly. You roll 2 dice and you move the sum of those dice. So what we're going to do is we're going to figure out all the different sums that can occur between 2 dice, and then what the probability is of each of those occurring. So you can see in this table here, we've listed out die 1 and die 2. So 1 and 1 makes a sum of 2. 1 and 2 makes a sum of 3. 1 and 3 makes a sum of 4. So on and so forth, all the way down here until we get all 36 possible outcomes. Then what we're going to do is we're going to count how many times each one occurs. So the sum of 2 occurs 1 time. The sum of 3 occurs 2 times. The sum of 4 occurs 3 times, so on and so forth. And we will then calculate probabilities on the next slide. So here's the sums: 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And 2 happened 1 out of 36 times. 3 happens twice out of 36. 4 happens 3 out of 36. 5 happens 4 out of 36. And you can see all the way through here. And the one that happens the most is 7. The most likely event of rolling 2 dice is a sum of 7, which occurs 6 out of 36 times, or 1/6. And if I sum all of these together, I'm going to get exactly 36 out of 36, a total of 1, because I've counted for every single event that occurred.